yeah, we'll get started with today's project, building the threading curves. Let me get my thing back up. All right, so here it is. And to start with this, I actually pulled in week 5's lesson. And just going to go through this for a little bit of review. So we started looking into the different ways to generate random numbers using either the rand function, stepping or kind of quantizing that to snapping it to steps, or using a noise function that would give us a bit more of a cohesive kind of natural pattern to things. Taking a look at that and then looking at it in 3D instead of one dimension, and then eventually using it to draw like a curved line. So if we look at this, flow lines that get extended in 3D space, this is actually what we use for a building block for this lesson. So if we just take, instead of this grid, we just start with one curve. This is, you can imagine like this is kind of the guide path that everything will be flowing along or following along. So just taking a look at how we built that, it was a pretty simple example, just a few lines of code, maybe 8 lines of code or something like that. So not too scary, hopefully, but just a bit of a refresher. So again, to draw a line with vex, you use this add prim function, and then this will basically add a primitive to your output geometry, and then you draw the line. Basically, you need to add points, and then to attach the points to the line primitive, or to the, to kind of connect them, you need to add them using vertices. So if you just add points, but don't use a vertex to kind of parent them or binds them to the line, they'll just be unconnected points in 3D space. Does that make sense? Just a bit of a refresher on that. So like if I get rid of my function here, we no longer have a line. The first point tries to get added to the line, and then it's just a line with 0 length, and the next point gets actually unconnected. If we do the same thing here, just multiple times, you'll just see that it's like unconnected. Boom, boom. So that's the purpose of using all of these functions, is basically to kind of parent them, or you're adding it to the line primitive, instead of just add point will just be an unconnected point in 3D space. So we extended that out a little bit using a for loop to build out, or to take multiple steps and connect them all to the line. And then did our random walk using this random function to just go, each step would be purely random, and then to do a smooth backbone kind of like a bird flying through wind, or just any, like a leaf or anything like that, just a bit of a natural drawing path. So what I'm actually going to do is just copy this code and just get rid of that review file for now, and we'll just get started in another empty geometry container. So I'll call this week 7 start. We'll make a single point and a wrangle. And I'll just press Control V to paste that code. So hopefully everyone's on the same page or knows about this. I could kind of talk about it a little bit if you're not caught up. But we're basically using a for loop and incrementing or counting however many frames our scene is set at, and then that will be the length of the line or the length of the curve, if that makes sense. And if you guys want to get caught up or just pull this in, can do a scene share. Swash, how's it going? Get the gist of it. Yeah, so hopefully it's not too, I don't want to start with something that's like too complex, but just for the sake of kind of speeding things up or starting with something. So, I mean, I could step through this a little bit. So if we, instead of using this position, basically each time this loop runs, we're moving the point a little bit. If you do plus equals, it will just add the number to itself. So if we add 0.5 each component or each axis, it will move in the positive direction. So you get a diagonal line. If you want to use the set function, you could move it along a specific axis or direction. And then instead of doing that, we're using a noise function to push itself. So the noise is generated based on the current position and then it moves. So it's kind of like walking through a noise pattern or a noise field. And then it's just adding the point to the existing line each step. So if we want to start doing some of this, why call create pose instead of just using P? You probably could use P. There's like one kind of there's a bit of a kind of confusion, I guess, with it, just the way that Vex is running. So the P is the currently processed point. If you kept moving it, you would end up with that point being at the end. Like we're generating more and more points. So I'm basically leaving this point right here at the starting point and adding, as our loop increments, this is the first point that gets added with the loop, and then so on. So if we kept moving P instead of making a copy of it, we would just start here instead of here, if that makes sense. Yeah, so if you wanted to, we could do a quick experiment. Take a look. Oof. Mess that up real quickly. So instead of this, we'll just do this, this, and this. So it's a bit of a, P keeps getting moved to end up at the end point, but because I've added it as the first vertice or attached it as like the first point in the line, then we get this weird kind of connection like that. So yeah, it's just a bit of a kind of gotcha, I guess, with Vex, or the way that I'm using it here. You could even think of this like, sometimes I'll run this like this. The very first thing I'll do is just remove the point. Should just be PT num. And if you want to, you could then explicitly kind of re-add it, and it's a little bit more clear. The reason you would do this is like, if you want to make more than one line or whatever, you're just using these points, the input points, as kind of like generators or starting points, and then you're moving it from there. This might skip extremely rapidly forward since P, it ends up all the way at the end, right? I think it would be okay to keep P at the end, but it would just be connectivity and stuff like that. You might run into some issues. So yeah, if you wanted to remove the point, and then instead of running things like this, we'll just leave that there and put that there. So what we're basically doing here is now just completely ignoring the input position or the input points. We're deleting them, and then we're just using it as a coordinate, as a starting point. So none of the input geometry is actually used in the output in this case, because I've replaced the function like that. All right. And then one thing to kind of keep in mind or something like that is that this remove point and add point and stuff like that, these don't really get executed in the order that you've typed them into the code. Like the code structure doesn't necessarily run where the first thing it does is remove the point, then it does all these. When Vex runs, it kind of reorganizes itself, and it will do all of the geometry deletion in like a final step, all the geometry creation in a separate step and stuff like that. So even though you're removing the point, you can still reference the point position and get the current point position. That's kind of a gotcha sometimes for people getting into Vex or stuff like that, is that this function is just queuing the point up to be deleted during the deletion phase. You could still reference the binded attributes from that geometry. All right. So if we're going to be building this curve and using it as like a backbone to get our stitching or threading built, we're going to want to know a bit of like the orientation of like the direction we're heading in, instead of just, right now we just have points in 3D space that we're connecting. Because they're connected, you kind of get a sense of the direction, but at the time that these points get created, you don't really know the direction or anything like that we're headed in. So one thing we can do if we want to kind of keep track of the direction we're heading in, we can make a temporary attribute, or I'm sorry, temporary variable. The reason I'm saying temporary is because when you declare a variable inside of this for loop, elsewhere in your code it doesn't remember it or it doesn't keep track of it. The scope of that variable is only accessible or valid within this loop. So if I say previous position, and then I set that equal to the current position before we move it, we've just basically made a copy of this into previous position. So then after we move it, we have our current position and the previous position, if that makes sense. If we want to visualize this or just kind of double check our work, I'm gonna remove this add point function and replace it with a variable that I haven't made yet, and then I'll just make that variable. So the reason to do this is that when you create the new point, this will be its kind of address or its index, just the way that you could refer to it. So if we want to add this point to the vertice and attach it to the line, we can reference it using the point number that gets returned when you call the add point function. So if I want to do another thing, like add a point attribute to that point, then I can reference it this way. So I'm going to call this the normal, or n. This is like the built-in Houdini naming convention for the normal vector. And we just need to tell it which point, or the address, or the index number of the point we want to add it to, and then the value. So for the value, we can do a kind of simple bit of like 3D trigonometry or 3D math that will be, anytime you want to create a vector pointing in a certain direction, you just use the from -2 formula. So if you have 2 points in 3D space, just build this out quickly, and you want to get a direction pointing towards that other object or the other point, you say the point of this position in 3D space minus this one, and then you'll get the direction to it, if that makes sense. We can check our work. I just use these spheres because it's a quick way to generate like a point and be able to move it around. If you want to, you can use this add node afterwards to delete the primitives but keep the points. So you still have this kind of nice transform handles with them. You have like visualizations of them if you want a little bit of like a thickness or something. And here I'll just say normal equals, we can use this op input 1p. So we get a normal, and it's pointing towards that object. So this is a bit of like a reverse order. You're saying where you want it to end up minus the current place that it is, and then you'll get the direction vector. So it's just the from -2. And then sometimes you'll hear people refer to something called normalization. So this is a process people use for normals. It's a bit redundant or whatever. But if you're thinking about a direction vector, you can see here that this in the x direction is like -6.9. The y is 2.3 or whatever. If you are making a vector or something that's purely representing a direction, sometimes people will do normalize like that. So what this is doing is making the length of this direction a unit length, or 1. The reason that people do this is if you're using it for orientation or rotation or stuff like that, you don't want it to represent like a scale or a strength or something like that. So you just want it to be kind of a unit or uniform scale. So it's like if you're doing this copy and transform or something like that, you want to keep the scale at 1 if you're just rotating something or duplicating it using like a translate. So this is why people might normalize something. For velocity or other vectors, you wouldn't want to normalize those because the length of them or the magnitude, this is another way to refer to it as just how strong the vector is length or magnitude. It's basically like the speed or just how quickly it's moving. So if you're just purely looking at a direction, you kind of want to discard all that information. So that's what this normalization is doing. Fit, float. I'm not sure about this fit float, but yeah, that's something you can do. So I'm going to do the same thing now for this normal attribute that we're going to create on this geometry. So we want to go use our same formula, from -2. So our from should be the previous position, and the 2 will be the current position. And then I think I just need to tell it that this is going to be a vector. I might have gotten ahead of myself here with this function. Let me just look it up. So I think I should have used set. All right. And I think I might have already messed the order of this up. All right. So it gets confusing to keep saying is like the reverse order or whatever. But so we're going from the current point position, pointing it to the previous point position. Hopefully that makes sense. So we're just getting these normals pointing along the direction that our curve is heading in. And I don't think I need this. And then if we wanted to keep these as a unit vector, we can just normalize them with that function. The first point, does it get, it should be getting set, right? So if we want to inspect these a little bit better. Getting ahead of myself here. Oh, okay, yeah, so we've never set the first point here. Yeah, I think I'm just leaving it undefined. But I think it should be okay for right now. If you want to, there's other ways that you can do it. Like you could add another condition at the end or something like that. But yeah, you can see even in my geometry spreadsheet here that it's just getting set to 0. So we have a normal vector that we're creating like so. Whoops, let me get back to my perspective view. All right. After the loop, set it to the second point's normal. Yeah, I think that's a good way to do it. I'm just trying to think about my code and the way that it's structured. But yeah, if you wanted to do it, that's a quick way to do it. To just take this second point and just use the same direction. So we get my drawing pad out. We'll just take a look at what we're doing right now. So we're drawing this curve. We're connecting points that are getting moved each time. And then we're keeping track of the direction like this. But if you want to make an orientation, or if you want to make like an easy way to define the transform of these points, just having a single vector or a single direction isn't good enough, because you don't really know like which way these are rolling. If you'd imagine like an airplane flying along this path, or even a camera or something like that, you don't know which way is up. Like if you're spinning around it, you know the direction you're heading in, but you don't know like the rest of your orientation. Sometimes people call it like a pole vector or an up vector or something like that. So this is the next thing that we're going to want to add. So we made the normal, we can visualize it like this. I'm just going to keep things a little bit more clear. So this, another way to refer to this normal vector, if we look it up here, the tangent of a curve, this is another good way to refer to it. It's like more mathematical, I guess. It's just a vector that's pointing in the direction of your curve. If we extended these out, one of these out in back and forwards or whatever, we'd get a similar kind of illustration. So the normal is just a Houdini convention kind of thing. To visualize it is set up pretty easily to do that. But if we want the pure like mathematical kind of label, maybe tangent is a little bit more clear. All right, so we have our tangents, set them to normal, and now we'll make another up vector, or another vector to keep track of things. I'm just going to set this at the top, like a global kind of thing. And I'm just going to initialize it, or basically set the default, or the starting value here, to 0, 1, 0. So we're just declaring it and saying that it's going to be y, or up in y. And then if we're defining it, or we want to add it to the geometry here, we can make something that's actually called a bitangent. And the way that we can do that is using a cross product. So the cross product is a pretty special, it's a useful operation. If you give it two vectors, it will like give you one orthogonal to it, if that makes sense. Let me just, we'll just add it here quickly. So I'm just going to comment this out and add it to the geometry. So if we look at a cross product of our tangent and our up, then you can see we have some bitangents. And let me get rid of this. So these are nice as they're pointing orthogonal, or it's like intersecting with the curve, if that makes sense. We can just take a quick look here. So something like that. This is the tangent here, and then this is the bitangent going the other way. Hopefully it's helpful. Another thing to note about the cross product is that the order of this operation is important. If we switch this around and go the other way, you'll get kind of like left-handed or right-handed coordinate systems. If you ever see people doing that kind of stuff, is related to that, I believe. For this case, I don't think it matters too much, but if you're writing like a really intense renderer or other kind of thing that like depends on a lot of other objects and stuff, you might need to be worried about it more. All right, so we have our two vectors right now. We'll just keep naming these so that it keeps staying clear. And if you want to be absolutely certain, you can kind of keep normalizing things like this. It's not the worst thing in the world. It's like just rather you be safe than sorry, I guess. And we'll just keep cleaning this up a little bit. If I wanted to here, I could just call this up. If we're just going to keep visualizing stuff. So N and up are internally used by Houdini. That's why I'm keeping them, or that's why I'm storing them like that. So if we just do copy to points, maybe just do the default file. You see the first one has some issues, but we're not going to worry about it right now. And then all of these others are oriented like that. If we get rid of the up vector, you can see it's having a little bit harder time, or it's not as clear as the orientation we want to provide. Everything is still kind of looking in the same direction, but the role of it isn't necessarily how we want it to be. So that's the importance of having these two vectors, the N and up. And another useful thing when you have these two vectors is that you can derive a third if you need to, using the same operation. I guess you can see the internal variables in the documentation. Yeah, I think it's not, I don't know the best place to have them. There's Houdini copy and instance attributes. It's like a somewhat complete kind of glossary. So this has some pseudocode and stuff like that they use whenever whenever you're instancing or copying geometry. All of these attributes can be used to influence it, and then depending on which ones exist and stuff like that, it will apply or create the final output using this kind of pseudocode. But I'm going to be doing more of this stuff in the code. I'm just doing this to kind of quickly like visualize or as an explainer. But for the final project today, we don't need to worry too much about them. So we have our normal, or we'll just say this is the tangent. And then we have the up, or we were saying this is the bitangent. And then if you want to make like a full 3D axis, you can keep doing just one more cross product. So now that we have these two vectors, if we do a cross product of them, we'll get this third vector to give us a complete axis. So I'll get rid of these set point attributes for the time being. Like I was saying, we'll just manage this stuff internally. I was just outputting them to kind of explain the thought process or to visualize them a little bit easier. So if we want to make the third one, that will allow us to create a matrix. And then we can use each of the local axes, this X, Y, and Z, to create a full 3x3 transform matrix. So we could keep using this set point attribute to visualize it. And let me just make it real quickly. So just say xform, or shorthand for transform, and you can fill the rows and columns kind of quickly using this set function. So if you want one axis to be the tangent, one axis to be the bitangent, and then the last third axis we'll be creating again using the cross product. And then that's just going to be the cross product of these two. Oops. Messed up a parentheses. Then we should have, all right, then we should have a full transformation 3x3 matrix. And we could add it to the geometry, and again, just double check ourselves. So we'll add it to this. 0 is just the current geometry. I'm going to call it transform here, because that's the naming convention that Houdini understands. And we'll just say this is the point and the value that we want to set. So now we have our transform matrix. And again, if we copy to points, get our file thing back here, then you can see that this is also being used to initialize or keep track of our orientation of everything. So without it, these just get the kind of world space positions, or they just don't have any orientation information. And with it is using the local frame of the curve. So if you've ever seen the visualization before, yeah, you can use that make transform function as well. Is kind of like this, what we're creating. So T is our tangent that we made first. B is the bitangent. And then no worries. It's good to know about the other shortcuts and stuff like that. And then this N is the third vector that they're creating. They just call it N or the normal. So that, hopefully that makes sense. This is kind of, again, another good visualization of what we're doing. So the reason, one of the really useful reasons to do this with a matrix and stuff is that you can apply twisting and change the, like, make rotational or scaling operations or stuff like that and keep track of them really easily. So to manage like a rotation in 3D space along a curve, it would be really difficult without using a matrix. You could do it using like atan, sine and cosine and all that kind of stuff, but you're working in like polar coordinates and a bunch of other stuff, and it gets harder to keep track of. And then managing like nesting multiple transforms is a lot more difficult if you're not using matrices. So that's one of the big reasons, again, that people will use these matrices to keep track of transformations. So if we wanted to visualize this kind of stuff, we'll just make a rotation. So what I'm going to do is, you have to be a bit careful of like the order of operations with your matrices. So if I do it, I'm going to do it the wrong way first. I'm just going to rotate the existing matrix. So this is the same rotate function we were using from last week to do the black hole kind of swirling effect. So you do rotate, then we give it the matrix we want to rotate. The amount you want to, you could do pi is 180 degrees or a half rotation, and then the axis that you want it to rotate around. So you can see it's not really doing what we want it to. Well, basically, the rotation to go along the curve happened first, and then we did our rotation around the z-axis as a second step. So if we want to switch around the order of operations here, what I can do here is I'm just going to press enter to get a new line. Then I can first initialize this matrix to identity, where this is just like a world space. Global frame is kind of the identity. It's just like an unused or unmodified transform. The reason to do identity instead of just 0 or to let it like try to initialize itself is that you'll get a scale of 0. So ident will give you 1 across the diagonals or just a unit scale. No rotation, but just a unit scale. And then we'll do our rotation to the identity matrix. And then as the final step, we can apply the curve frame, the local frame, just using a multiplication operation. So if we look at pi here, we divide it by 2, you can see we're rotating. Now, I might have picked the wrong vector. Let me just set this to time. Yeah. So if you look, we're rotating using the curve space, but we're going along the wrong axis. So in this case, when I constructed my transform, I did tangent in the first slot here of my set function. So this is like x, y, and z. So if you want tangent to be z, you can just kind of shuffle these around, if that makes sense. And then we're rotating along the curve. Does that shuffle stuff kind of make sense? It's kind of like a kind of hack or whatever to modify transforms, or like kind of coordinate spaces. The variable we called tangent is really the normal, or what? I'm calling these kind of trying to stick with a naming convention. So tangent for curves is usually called that, the way that I've named it internally using the variable. Bitangent here is just a direction that intersects or is perpendicular to your tangent. And then the normal, or the third vector, the third axis that I'm generating, here they're calling it n. I think other people call it different stuff. Like I said, it's not, this third vector isn't 100% necessary in all cases, because if you have the first two vectors, you're good to go. Basically, once you have two directions, then you will always be like referring to the same transform. If you just have one, then you might be spun around a certain direction. Once you have two, then you can get the third quite easily, and you'll always be referring to the same direction. So what we're doing with this shuffling of space like that, if we just take our object here of the default cube and do these vector to float and float to vector, if we just fill these the same way like that, we don't get any change between the input and the output. If we swap this z and x, just turn that stuff off, then we're kind of like getting into a mirrored dimension, or switching into a different coordinate scheme or something like that. So this is kind of what I was doing with the way that I constructed this axis. So you're just setting which direction kind of your curve is heading in, if that makes sense. Can do it using the file, and then instead of default, if you just do def axis, then you'll get a little gnomon like that. And then if we look at our curve here, if we don't do the rotation for now, we'll just leave it as it is. Usually I like to have the z-axis going along the curve. It's just a personal preference of mine or whatever. But if we switch this back around, just do a different order here, then you can see that the z is getting set differently. The last vector that we're using is then becoming the z, if that makes sense. So just Control Z to go back, and there we are. If you want to get up to date, do another update with this file where we are. So if we use this rotate instead of just doing a constant like time, this is the same value all along the curve. We could use this I variable or incrementer. It was just the current iteration of the loop, or the current point number on the curve that we're at. So if I say time plus I, then you can see we should start to be getting some kind of spinning along the curve. With the I here, if you like divide it by 12 or however much you want, this is just going to change how quickly you're spinning or rotating along the curve. So maybe, let me just adjust my step size here. So we're just not going to move as far. You just do multiply by 0.25. So this is just shortening our curve. And then I think with this I, if I divide it by that. So before I added the decimal, this is thinking everything is an integer. So we're getting this stepped kind of result. So if you just either set one of these two numbers in your division operation to a float, if you just add a decimal, then it's smart enough to kind of cast that operation to a float operation instead of an integer operation. So that's pretty cool. Amazing. Endless possibilities. That's the idea. This kind of stuff is really useful to know about with the basics of vector math and stuff like that. They have a lot of nodes in Houdini. We used to use this polyframe. This could be used to construct these same axes pretty easily, and then orient along curve is a newer one. So all of these can be used to create, they actually have this built in here to do transform. If I plug it in here with, I guess I could do it this way. So I'm just reinitializing a transform, and then they have some similar operations you can do here. But knowing about all this stuff and how it's constructed using vex is very powerful. Spinning used for throwing arrow. Yeah, it could be used for a lot of different stuff. Tons of, it's kind of endless possibilities. But yeah, so a lot of the things we've been creating, even stuff is constantly being added by side effects. Like they have this projectile ballistic path. This I think got added with 18.5 or maybe 18 very recently. But if you look at this, this is used to make like a kind of impact hit for an explosion or stuff like that for the trails that go off. But if you remember from the first week when we were doing the bouncing balls and stuff like that, this is a similar equation. So like fireworks or just anything that's like affected by gravity over time, this thing could be useful for it. If you go inside, they're doing a ton of stuff inside of here. Somewhere in it you could find the vex kind of operations that they're doing. I guess they might have been splitting this out into a pretty complicated structure. But if you get the idea is that using this kind of vex, it just gives you the power to create these tools that could be used for arrows or for cannons or projectiles or just tons of interesting effect stuff. Like this thing right here, doing sewing operations, knitting, they do have a lot of tools to manage things from more of a high level without getting like your hands dirty too much, but it's super useful to know about the actual vectors all the time, because you might run into a situation where like your orientations are messed up, and then debugging it if you don't know they managed to make vex complex. Yeah, all of the more recent tools that they make, I think they're just handling so many edge cases, like if attributes don't exist or they don't want to overwrite attributes if you've already had them, or that ballistic path, you can add attributes on your geometry to influence what's happening. So like, because they've built in all of those extra little utilities, it becomes a bit complicated. So I think they don't really intend people to go in and mess with this too much. So that's why they've built it out kind of like that. All right. So we have the curve. Yeah, tool needs to take a lot of the scenarios, and yeah, so it's just if you like look at this kind of code we're generating for learning purposes, or in your own time, you're probably making code that's pretty concise and it's just designed to do a specific thing, and you're expecting like a very specific scenario. But if you're generating like code that would get used in software by the entire community, all of the side effects, customers and everything like that, they're trying to handle every single edge case. They're trying to optimize stuff as much as they can. So they're not making it like as clean for the beginner or just for someone to jump in. It's more of, I guess that's part of the reason as well. I don't know. I mean, it's not necessarily stupid. Just any people with fresh eyes, whenever you jump into those networks, it's a bit of a, it just makes your eyes glaze over and you fall asleep, kind of. All right. So we'll, again, get out of this, and we don't need to set this attribute right now. I'm just doing it as a quick way to show you guys what this Xform is doing and why we're managing it the way that we are. So we want to make a fresh identity first, is just like a world space. And then you can rotate it using this, and then you apply the final curve space to rotate this direction into curve space. You do this final operation. So if we want to, again, build this out, we want to keep doing everything in this one wrangle. we're going to want to start adding more lines. So what we could do here is like do int j. When I start nesting loops, I'll usually start with I and then go with j. And then if you do another one, you do k. It's like a standard kind of like nesting way to keep track of your loops when you start putting them inside of each other. So this one might be the number of curves that we're going to make, like the number of threads. So here, there's one main curve everything's going along, but then we're rotating or spinning a bunch of lines around that baseline. So let's just say maybe 2. And then we'll just keep with the same increment. And then getting some green lines here, and a bit of a warning flag. So it's just complaining that I haven't initialized the variable. So just like I did up here, is a good idea to set these to 0. Just to be clear, otherwise people might not know what number you're starting your count at. And then if we want to just visualize stuff, I think we can start with an add point. And we'll be adding things to the current geometry. 0 for just myself, essentially, and the position. So if we look up here, we're doing pose for the current position along the line. We can just say pose, and we just get a bunch of lines where we already were. So we haven't moved anything. We're just adding more points to the existing line. So we want to move these. This is where the matrix and that kind of stuff gets pretty handy. So if we say pose plus just a certain vector. So I'm going to say x is 1 and then multiply this to apply or to transform ourselves into the curve space. Then you can see we're getting a spiral. So does this kind of make sense? What this is doing here is saying set. We're saying just go one unit in x, but after you've rotated into the curves space. So we're basically in the origin or in world space saying move 1 unit in x, and then by multiplying ourselves into the curve space, then that x is getting kind of represented here by n. Because we did the rotation step at the start, our matrix is already like spiraling along the curve. If we want to look here, comment this. No rotation. So all this x is doing is just a offset, but kind of in curve space. And then once we rotate. So if we want a little bit more control over this, we can do our matrices, matrix operations inside of this for loop. The reason you might want to do that is that when you're rotating like this, then you can do a unique rotation for each point. Or again, what these points are eventually going to be is individual threads. So by default, we were just using I, which is each step of the curve, to increment our rotation. But we could add a random number that's generated using j, or this thread. This is kind of your thread ID. So if we do it like that, we get a random offset you probably want to multiply this by pi and then by 2 pi, so that this random number gets scaled basically from 0 to 360 degrees. So the rotation around your axis here is specified in radians. It's a bit of a gotcha, but if you want to be saying spin anywhere from 0 to all the way around, you just say 2 pi. So this random number we generated is a number between 0 and 1. If we don't do that, and I create a ton of little points, you can see that they're all constrained to only rotate between 0 and 1 in radians, which isn't a full rotation. So if we do pi, then we're generating random rotations, a half circle or a half rotation, and do it either order. It doesn't make sense to do one or the other. It's just whatever's up to you. 2 pi or pi times 2 is the same thing. You guys are starting to see where I'm headed with it? So we're rotating randomly now for each thread or each child point or each point in this loop. Another thing you could do is how much you're offsetting from the curve. So here we're just using 1 as like a unit vector or a normalized vector. But if we wanted to modulate the amount here, we could say maybe this is like dist from, you could just say main. I don't know, sometimes I don't want my variables to be super long. It makes the code like you have to scroll too much or whatever. So we just say this is dist, should be okay. And set this equal to a random, again, just generate a random number from J. I'm gonna offset it so we get a unique number. And then you could put this, should be able to put it right here. It should be okay. So we have a pretty cool randomization now, things going along the curve. All this talk about pies. So we have our distance that's being randomized like that. If you want to do a bit of like a weaving or kind of sewing motion, one thing you can do is modulate this distance over the length of the curve. So we could say dist plus equals a sine of I. And again, you might want to change I at some point. I think it's too high of a frequency, like it's fluctuating too quickly. It might also just be because it's an integer. If I multiply this by like 0.1, then you could hopefully see what's happening. Could do it even lower. So as these go along the curve, they're kind of expanding and contracting. So if you're imagining like the way that you see some thread, depends on the structure of it or whatever, I guess, but there's portions where stuff like dips down inside of it just to get other things like overlapping it. Like if you're braiding stuff, you're always putting something over another. Certain ones, this might just be a twist, but certain threads, they have more of a complex like braiding operation. So if you just want a quick thing to simulate that, you can start to use a sine. And then again, I might want to offset my sine function to be unique for each of these thread points. So I can just do that again by, whoops. Let me just get rid of that. Oh dear. All right, we're back. So if we just add a random, again, just base a random number off of, j. So we want it to be unique to each point or each time this loop is running. And this one, again, we want to multiply it either by pi or by 2pi. The assign function is the same to reference like random positions in it between each repetition. You want to be scaling it to 2pi. So now each of these is offset just the way that they're expanding and contracting. So maybe if we don't do this initial, we just set this to 1. We could set it to 0.1. This is like a master radius kind of now, or 0.025. I think, I see what's happening. So my sine function here is adding to everything as well. So if I divide this or multiply it by a smaller number, we'll just get things that are closer to the curve. So if you guys want to get caught up, do another file transfer. And then we need to start thinking about how we're going to connect these lines into curves. We have a bit of a problem here. So at the start, you could see I made my initial primitive here that all of the main points get added to or connected to. And we did that before we entered any of these loops, because we just want one line. So if I tried to do my add prim function up here, we would run into a pretty big problem. We would get a ton of primitives. Does that make sense? If you say add prim 0, or you just need to tell it what type? Polyline. None of the points get added, but if I go to my geometry, you can see without that, we have the one curve, but because I am adding the prims here, this is happening 32 times, and then this loop is parented, or it's inside of the main curve structure. So basically, at each point of the main curve and for each point of the threads, we've made 2,368 lines that don't have any points belonging to them. So this is going to be an issue, because we don't want that. We just want like 32 lines. So what are we going to do? Get rid of that. That's the first step. So we could do, like up here at the top, these lines, we could say this might be thread prim, but then we've just made one. So I could say this is 1, 2, and add them like that. But this isn't a very good idea, right? So as you do this, your code it just becomes a pain to manage all these. If I wanted to say, let's go from 2 threads to 32 threads or something like that, it's going to be a ton of tedious typing. It's going to be a pretty big pain. So it's not a very good idea to do that. So we can use a new data type. This is going to be, just do vex language reference. So again, with data types here, we've been using a lot of these. Some of these we haven't used yet, but we've definitely done integers, we've done floats, we've done vectors, we're doing matrix 3 today with the 3D rotation. We're going to use a new thing called an array. This has its own page here. If you guys want to stay on the same page, you can get it there. What this basically does is it lets you set a list of information. So what I can do is use this variable to contain a series of information. So this could be a series of strings. Here they're using it to store 2 paths to 2 different textures. And what I'm going to do is use it to store all of these thread primitives. So instead of setting things up like this, I can just make an array like that. If you're just trying things out for the first time, you can debug stuff by adding it to the geometry like this. So I could just say something like this. And I think this, when you set the attribute, it gets set up like that. So this stores basically a list or a series of integers, if that makes sense. If you want to tell it how many things you're going to store, you can use the resize function. So you could say resize. And then the length that you want to resize it to. I might need to keep doing this business. I might need to fill it with something. Let me see if this. All right, I'm getting ahead of myself here. So if we just want to, let me do it this way. So I'm going to modify this array first, and then we'll visualize it using our function at the end. So I want to resize this variable. We don't have a way to visualize it yet. And then I'm going to add my prims to it. So you can use this for each function to iterate over every element of an array. So if I say int thread, and then this one will be threads. I think I've put that bracket the wrong way. So what I can do now is add the primitives. So we'll say threads whoops. Like that. And if I go over here, you can see we have our extra primitives that get added. So we just have one thread. 4 threads is a much easier way to keep track of these. And then anytime I want to know about these, you can use the square brackets to retrieve an individual entry from your array. So if I say, let's just do I at So I'm going to set up the variable or the attribute now to visualize the variable. If we go over here, looks like it still isn't, it's not filling with values the way that I thought it would. I don't know if there's the easy way to copy things over like that. I'm just going to get rid of it for right now. Whoops. Uh-oh. I don't know how that happened. Oops. All right. So let me think of a different way. I'm just going to keep going ahead and continue to build this out. And hopefully it will get easier to visualize there. So I'm going to clean up a bit of this white space of the code so we can hopefully see everything. Oh dear. All right. So we're close to seeing everything. We can scroll from the top. We don't need it right away. So down here, instead of this being a for loop for the total number of threads, we can use this for each again. So we can say for each. We could keep our enumerator as j if we wanted to. And then this will be threads. So this is just your index kind of counter as you're going through your array. So you can see as that changed, somehow we only got down to 2 spirals here. I don't know if this is something I did wrong. Should be getting these should be unique numbers for each of the threads. Let me keep going and see what happens. I don't know if this. Let me turn on these. Looks like these are getting the same things. It might be when I'm doing my for each, I've messed something up. Let's take a look. There's a couple different ways that you can run this for each, and I think I want to do it this way to keep track of the index and the current value. I think that was the issue, was that these needed another. Okay. So this thread is the kind of primitive handle for this line that we've added. And then J is just the counter for which entry of the array you're accessing, if that makes sense. We can double check this or we can continue to move forward. So the add point here, this will store this as a variable. So we'll call it like thread PT. And then I can do our add vertex. And we want to use 0 for the current handle. We want this one to be thread. So this is pulling out the current element of the array that we're accessing. And then we can just use our thread PT. Uh-oh. We have a mystify. This should be, this is the mystify screensaver. I might end up doing this a different way. Yeah, so I'm just gonna go back. I'm gonna retreat a few steps. Sorry about this. So we'll go back to when we were using a for loop here. And then what I'm gonna do is just replace this using the length function. So this is a different way to see how many entries you have in your array like that. And let me try to move forward with this. So this, again, we'll call it the thread point. And then when I want to add the point to the line, we'll say, we can use J for this. So we'll say threads J, and then the current point number. Could be something up here that I did wrong when I added the primitives. Let me, it might be there. Let me get rid of some of this stuff. I think the twist, yeah, I think I might have broken it with the twisting stuff. So we'll go, let's get rid of Alkama. How's it going? Something. You're late. You're just in time to see me mess up a lot of stuff. I've broken something. So I might, I might 7 to see the resize. Yeah, I can try that. Let me also. It's changing the amount of primitives I'm generating, but I think this here was my mistake maybe. So I think adding them to the array, this was using the current value, which was initialized to 0. So I just kept adding blank. Like I kept adding all these prims to the same entry of the array, if that makes sense. I think I should have caught that earlier when I was visualizing it. So we could try to do it again here. I think this isn't showing up because of a different reason, because I'm removing this source. So this is now working. So this attribute that you're adding won't show up on the points that you're generating. It will just, when you use this at syntax, it will just bind it to the current geometry. So I think that's where I had gone wrong. So if I do thread here, that's only accessing the first entry. So it keeps filling the same 0th entry, if that makes sense. Sorry, it's not a very good way of introducing you guys to arrays. But this, basically I confused myself with the syntax of this for each method. So this is the array, and then this is the current existing element. So it was always just full of zeros. And then when I said add to the 0th element, it just keeps saying to the same line to overwrite itself like that. So if you use J, it should work. And we could probably go ahead and do the same thing down here and be okay. No change is pretty similar functions or ways to do it. The added benefit here is that instead of saying threads J like that, you can just say thread and you'll get the same result. So we add our rotations back in and we're in better shape. Sorry about that. Got off the rails for a little bit. So we can get rid of that source point again, and if we want to, we could even comment out this for a second, and this one as well. And we don't even need this new point as well. So what we're basically doing is we're hiding, or we're making the source, the backbone line, invisible. We're still keeping track of its position using this pose, but we're not marking it, or we're not creating that center line, if that makes sense. If you guys want to get updated, here's the file. So just playing the animation now, we have a few things changing over time. I'm going to get rid of this time global right there. And then the only thing we're doing now is growing everything, or moving it along the curve based on the frame. And I'm also going to add this back in, the dist. I'd taken that out for debugging purposes, or just to see what stupid mistakes I was making. But now we're able to modify things a little bit more easily. So this gives us a bit more control over the distance from the baseline over the curve's span. If we want to, we could add this random back in. Just is up to you, however you want your stuff to look like. So the big reason behind all the stumbling and blundering I did is that we just have a single number now that we can change if we want to control how many other threads we have going around our curve. So before, we would have had to make all of these primitives the problem was I was using the wrong, so with the for each, there's these two forms that you can use, the simplified form like this, and then the enumerated form. I was using the simplified form, and basically what that does is it iterates over every entry of the array. Let me visualize this again. So for each entry in your array, the for each function will loop. Then this thread will inherit the current value of the array. So by default, all of these were getting initialized to 0 because I had just resized it. I thought that this was the index or the enumeration number. So I kept thinking that I was like filling my array with the primitives, but instead what I was doing, if we replace it here, was just rewriting over the 0 value. Because I thought that this, which is the current uninitialized, or just everything in the array was 0, so I kept rewriting over the 0th entry of the array. Does that make sense? I wasn't changing the position. Using these square brackets here, you're saying you want to write to a specific entry of the array. And this is basically saying that, because everything in the array is equal to 0 at that point. So instead of this, if I wanted to write to like the third index, this is 0, 1, 2, 3, you can do it like that. This is just what entry of the array you're going to write to. And I thought that this was the index, like the current element I was indexing, but instead it was the actual like value inside of the array, if that makes sense. So we have this array called threads that's each entry in it I'm calling a thread, and I was basically skipping a step. I wasn't setting it to the right value. So instead of that, you can use J, and then you're storing the right numbers. If that, hopefully that's a little bit more clear. So just get rid of some of this stuff. We're back. All right. So yeah, now we have pretty good control, pretty flexible to set how big our array is going to be, and then we fill it with line primitives, and then we can later loop over all of those line primitives and add the thread points to them using this add vertex function like so. So it's hopefully a little clear, a little more clear. Hopefully you could see we're getting closer to the final target, the achievement. So now we just want to add some kind of per curve expansion and stuff like that to have it like it's spinning or weaving the thread over time. So we can do that just based off of the current time like this. But yeah, we can just do it using the current frame, I think. So we have this distance variable that we created that's just going to control how far away from the curve we're going to be placing these threads. So we added this randomness to it. If we want to turn the randomness off, we can do that. And then everything is the same distance away. We were also modulating things with this sine function to mimic, maybe this should be a higher frequency, kind of to mimic weaving or stuff like that. If you have a ton of threads, this kind of stuff happens as like, you just get the overlapping things. Sometimes use this wire. If you just want a quick way to visualize thickness, this wireframe node is quicker than like polywire or other stuff like that. So this is just controlling how quickly things will dip in and out with this. I'm going to disable that as well. So everything is spiraling the same distance from the base curve right now. If we want to further modify it, I'm just going to use this dist, and let's set it equal to a fit function. We can take I, and we can fit it from, these frame. So what I've done right here is say when this iteration or the current point number on the curve is equal to the current frame, scale everything by a radius of 1. And if it's 12 frames ago, set the scale to 0 or the radius to 0. So over time we get this kind of tapered cone. We're basically using the global counter. This is the current point number of the curve, and we're saying from the current frame to 12 frames ago, taper it from 1 to 0. Does that make sense? If you want a nicer fall off, you can use this smooth function. It's a bit of a gotcha. You set the first two arguments to 0 and 1. And then you just get, instead of like a linear, it is kind of like a ease in, ease out, smooth step function. And then if we, instead of overwriting distance like this and just setting it equal, what I'm going to do, sorry about that. What I'm going to do is just do a plus equals. So we'll just use this to only expand. So if I turn it off, no change. All that this is doing is moving the newly created lines further outwards. We can add in some of the stuff we were doing previously. And you can start to see the final effect. And if we want to add the previous stuff happening, like floating away of that stuff, I'm going to reuse something of this function. I'm just going to overwrite everything again. So we're looking at this. But instead of taking the current frame to 12 frames ago, what we can do is take like 42 frames ago to 56 frames ago. And then we have a funnel happening the other direction or at the other end. And we could do plus equals here. But if we do that, we're changing like everything. I guess we're okay. Yeah, I think we're okay with that. So we can leave it set up to this way. But this isn't super natural yet. It's like a bit too kind of robotic that all of this stuff is like you cut it with scissors or something like that. So what I ended up doing here was individually offsetting time for each of the threads to get a nice kind of more natural like sewing motion, just to make it look less like mathematical and just a little bit more natural. So what we can do is make another variable, and we could just call this like thread frame. And similar to the way we did this with previous position, you can just use this to make a copy of the global frame. And then can use it and just replace these fall-offs with it. And we're in the same thing. But if we want to now, we could modify this a little bit. In E too much. I got too excited. No, I don't know why, but this, when I make my UI bigger, like the cursor doesn't always place, it doesn't always like place the carriage where I think it is. So what I'm going to do with this is just offset time or the frame number randomly for each thread. So if we want to use J, that's the current index. It's unique for each thread. And I just offset it to keep all of these random numbers we're generating from it unique. And then this number gets generated between 0 and 1. If we use parentheses and subtraction, this will let it be centered around 0. So now it's going up from a range from negative 0.5 to positive 0.5. And then I just do a multiplier at the end. So we have a bit more breakup here. So if we multiply this by 0, everything is tapered at the same rate. If we do this, we'll have like a 12 frame variation from when threads start and stop, kind of lifting off. We just get a little bit more natural that way. And then if we, Cyber Slain, slamming in here with the pogars. So then if we just don't want to show or draw all of these curves, what we can do is say, there's a few different ways to do this. I'm going to rearrange some of my code a little bit so we can do it a bit more easily. So I'm going to get rid of this sine function for right now. I'm going to get rid of that random, like that. So we're just visualizing more of like the mask, and you could you just start the distance at 0. So we know everything will be between 0 and 1 right now. And then when I'm making my point and adding it to the line, what I can do is say, if the distance is greater than like 0.9, however accurate you want to be, I want to do this less than. So we're only going to draw or attach the point if it's within a radius of 0.99 or a threshold of 0.99. And then what I can do, like after I've done that check, I can start to do my sine wave modulation. And we can also set this random if we want to inside of here. Arvid, how's it going? Thanks for stopping by. Doing some very technical Vex programming today. So we can add this as well if we want to randomly modulate each of these. So you could do, there's different ways you can do this as well. You could try, instead of like multiplicative, you try additive. So you get a bit better spacing, maybe. You could play around with the amounts and stuff like that. It's up to you. I think this is a bit too many threads. If we want to go up to the top or the start, maybe just a little less might look a little bit more natural. If you want to play with these ranges, you can type in different numbers there. So we'll start our weaving or fading in over like a longer duration. It's pretty good. Want to clean this up, I'm just going to get rid of that. And we're a little, might be a little bit, pretty big block of code, but it's a little bit more concise. So yeah, and then of course, like the whole thing is Vex, is just starting with a single point. And then all of the animation is happening inside of here. So, and even the geometry creation and stuff like that. So I'm just using these source points as a signaler of like how many curves to draw and where to start them from. So if I duplicate this point out in X or something like that, then we could be weaving multiple strings or strands or stuff like that at once. You'd use a grid as well. This is all based off of kind of like a flow line visualization thing I was making. If you had some guide geo, you might want to break this out into more than just a single wrangle. You might want to split it out into a few steps. But basically, instead of this curl noise function here, if you made like a vector volume, then you could walk through that vector volume, very similar to how the trail SOP, the volume trail SOP works. So if you have the pig head, you wanted like vectors to flow around him, you could do some similar stuff here, I think, that we were doing. So we look at the normal. That's what we get. You can keep using this cross product we were doing at the start of the stream today. So I'm just going to do the normal and up. And then you get like this spinning stuff that's rotating along the surface or lying along the surface. And there's different ways to do this. You could just do scatter. So these will all inherit that direction that we were making. So I'm just going to kind of blanket him in those points. And then if you do just VDB from particles, that's a quick, yeah, you could use prim UV as well. That might be even faster. So what I'm going to do with this VDB, I'm just making a volume. This stuff should be okay. Let me just make it a little bit higher resolution. And instead of the distance, we can use it to store the normal. We could call this vel. And you can do a quick visualization here if you just do the slice with the volume trail. So this is doing a similar thing that I was doing in that wrangle, and just walking through the velocity field. In this case, we were using a noise function, but we could kind of rewire it if we want to. So I'm going to do another scatter. And then this is just going to be like how many threads we're going to draw. We can take this auxiliary input here, and Steffi Fung, how's it going? What we can do with this is, instead of using a curl noise here, we can use this volume sample V, and then this will just give us the direction. So we want to say from this auxiliary input and from the 0th or the first primitive. 0 is like the only primitive. So we have one volume, so it will just be index 0. We're deep in the Vex exploration. So every Sunday I've been doing a workshop for a few weeks that been building on different more technical stuff inside of Houdini. And then this one today was a pretty mathematical, pretty deep one where we were looking at like matrix transformations in different coordinate spaces and stuff like that. But yeah, we're making this kind of knitting stuff. I think I basically kind of baked in like a pretty big global scale for a bunch of this stuff. So we would either have to redial some of these operations, or we could make the pig bigger. But basically our spin radius here is way too big. So we could do maybe a final multiplier distance. So we're not braiding around a thicker area. Fun enough. The Vex ones are easiest to follow and understand. Yeah, I guess if you're not, it depends how you're approaching it. If you're approaching this from a programming background, it's probably making like more sense if you're math focused. But if you're just used to Houdini using the nodes, it's probably a pretty deep dive into the Vex stuff. So we can change also how fast we're walking through the volume field. If we do that, then we're just, each step we're taking is going to be a slower or shorter distance. And we'll start to see more of these little spiral drawers. Could make them maybe a little bit longer. And if we change like this scatter here, we could do more of them. You could also play around with the method here that you're generating your like vector field. It's crazy. It's the kind of the power of Vex. Once you get more and more comfortable with it, you can start to build these setups that are pretty flexible or pretty like optimized for speed and everything like that. So it's a pretty good thing, like in terms of performance. A huge point scale visualization. Yeah, that was something I was doing a while back when I was just doing a single line or something. It was hard to see them. If you go into the geometry guides, that went up to 15 or something like that, but you could go, you mess around with it. So I was just going to go in here to this vector field where the directions we're generating. I think you can get even fancier here if you just keep doing the cross products. So this will be original normal, and we'll make a copy of our current normal, and then as like a final step we can do another cross product between the normal and the original normal. And he's flying, he's going the wrong way. If we flip it, I think just maybe the order of these operations. Like I was saying, the cross product, when you do it, the order that you do your arguments of the cross product is important. Then you could get like a downward direction. So if you're doing rain flow or stuff like that, this technique can be powerful. And then when you create our curves, they're going that direction. You could also do other things if you just do polyframe. This one. By default, if you do like first edge or something like that, sometimes you can get interesting weaving, constantly doing the vector system thing. So if we pump this in, this will just try to derive directions based off of the primitive connectivity, or like the winding order, the primitive numbers of your mesh. It will store that as a vector. So if you want like paneled stitching or stuff like that, sometimes you can get interesting things that way. Let's try this with our wire. These might have been too big. But you can do this. If you're starting to get into crazy high numbers of curves, if you just do attribute create and make a width and set that to a low number, and then you just go up to your object level, and under miscellaneous, show open curves. Then you can visualize like a nice finer thickness, and it's a bit faster than that wireframe. So you can keep pumping this. You start to have an idea. I didn't really set this up intending to apply this to other geometry. So it's a little bit of a mess, but you could probably make an interesting animation of like a sewing or something like that happening to some geometry. So if you guys want to get up to date, here's the latest.